Hello, hello. We are looking at Lecture 16, Learning Objective 10. We're going to be drawing orbital diagrams and our electron diagrams in this particular part of this time. So I'm very excited to talk about electron configurations and orbital diagrams. So let's start with our electron configurations. So when we have our four quantum numbers, they are going to be used to represent all the electrons within an atom. And we can also use those quantum numbers and the orbital designations to determine our electron configuration and orbital diagrams. So electron configurations and orbital diagrams are kind of like a visual representation of our electrons from our quantum numbers. Okay, so they're going to show where electrons are distributed within the atom. So they're going to show what orbitals they're in, what subshells they're in, what shells they're in. And we always show our electron configuration or orbital diagram as our ground state. So we're looking for the most stable, lowest energy state. So we always show the ground state for our diagrams and configurations. So we're going to put electrons in the lowest possible energy states. Keeping in mind that we can only put 2 electrons in an orbital. So we can't just cram all the electrons into the 1s orbital. It won't work that way. So we want to put electrons in the lowest energy state, and then as we get more electrons, we put them in higher energy states, making sure that the lowest energy states are filled before we go up to higher energy states. And this is going to keep our lowest energy state for our atom. And of course, there are going to be some exceptions, which we will talk about. And it's going to be based on electron repulsion and stabilization effects. Okay, so let's start with just an orbital diagram first, because they are easier to look at. And we have already kind of looked at them. So our orbital diagrams are where we have our electrons in boxes, and they're shown as little arrows. So I guess I should put orbitals are in boxes, or orbitals are boxes or lines. You'll see them as lines as well. And electrons are shown as arrows. Okay, so we'll indicate our spin up or spin down, um, keeping in mind our Pauli exclusion principle, and keeping in mind our off-bar principle. So we need to keep in mind our off-bar principle. So that was the filling or the energy relationship between our orbitals. So we have spacing out of our subshells as we have more electrons, so, because there's more repulsion. So we have an ordering of the energies where we have 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So that is how, or the energy ordering of our subshells. So we need to keep in mind our off-bar principle, our Pauli exclusion principle, so here, our Pauli exclusion principle, one electron, or they'll go with the first electron, added to an orbital, is placed spin up, the second spin down. And there's a maximum of 2, so we won't do any more than that. There is also something called Hund's rule, and this states that if we are adding electrons into an orbital diagram, we need to add in electrons to our orbitals singly before adding them in doubly. So if we have a subshell, and that subshell has several orbitals, and all of the orbitals are degenerate, so for a subshell with degenerate orbitals, such as 2p, for instance. 2p has 3 orbitals. Each of the orbitals are going to be the same energy, so these are going to be degenerate. When we add electrons in, we're going to add them into the orbitals singly first. So we'd add it in spin up, spin up, spin up first before we add an additional electron. And only if we run out of orbitals will we then go in and add. So only double up if you have to. You do not want to go to a higher energy subshell. So double up before you go to a higher energy subshell, but just keep in mind that you don't want to do, so if we have 3 electrons, for instance, in our 2p, if we have 3 electrons, we want to write them like this. not like this. This is correct. Incorrect. Okay, so now that we kind of know the rules of doing um, our electron and orbital configurations, let's actually look at the electron configuration of a species. So let's take phosphorus, for instance. If we look at phosphorus, sorry, one second. Look at phosphorus. When we're thinking about phosphorus, we want to look at how many electrons phosphorus has. And then once we know how many electrons it has, it's 15 electrons. So phosphorus, no uncharged phosphorus, elemental phosphorus, has 15 electrons. So when we're doing an orbital diagram, we want to go ahead and draw out our 1s, our 2s, our 2p, 3s, 3p. And of course, we could also write them to the side. Write them to the side instead. And then we're going to add electrons in. We have 15 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That gives us our orbital diagram for phosphorus. If we want to make it truly accurate, we'll put an energy designation or showing how the energy is changing. We can look at calcium as well. So calcium is going to have 20 electrons. So we're going to do the same thing. Our 1s, our 2s, 2p, 3s, 3p, 4s. Add our electrons in. 1, 2, 3, 4. You can also add them as half. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, now I know where to stop with both of these because I looked at my periodic table. So remember, with our periodic table, it tells us information I've drawn this like 10 times now, but it's very important. So if we were to look at calcium on the periodic table, it is going to be right here. So I know that its outermost electron is going to be in the 4s subshell. So that's why I went to 4s. If we look at phosphorus, phosphorus is like right here. So I know that its outermost electron is going to be 3d. So we can use our periodic table to our advantage to save some time. Okay, that brings us to electron configurations. Electron configurations are just like orbital diagrams, but instead of writing out boxes, we're just going to write everything in terms of what subshell it's in. So if we looked here, we have 2 electrons in our 1s. We have 2 electrons in our 2s. We have 6 electrons in our 2p, 2 electrons in our 3s, and 3 electrons in our 3p subshell. So we're just using subshells, not orbitals, in an electron configuration. And we write them out. We write our subshell, and then as a superscript, we write how many electrons are in there. So our 1s has 2 electrons. Our 2s has 2 electrons, so we write 2s2. Our 2p has 6 electrons, 2p6. Our 3s, 2 electrons, 3s2, and then our 3p, 3 electrons, 3p3. You can do a very similar thing here. 1s, 2 electrons, 2s, 2 electrons, 2p, 6 electrons, 3s, 2 electrons, 3p, 6 electrons, 4s, 2 electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, that's it for this video. See you guys in the next one.